She needs us to record today. I think it's going. Yeah, it must be. There it is. There's this mixed bag review we can do today. It kind of walks through the different chapters or different kind of the big concepts. So we'll walk through that. It's got a few nuances in it. The other thing I wanted to tell you is I put in place, if you go to Schoology, let me record or show you the screen. I just added it around 5 to 1 there. Kind of this morning I was collecting a group of stuff for reference material. And if you go to the materials page, which should be your landing page for Schoology, now I gotta think of where I put it in. I put it in the May 7th bag, the May 7th folder. And there is a folder that shows AP Calc formula sheets. So I just kind of dropped in there all the good formula sheets. I thought this derivatives and anti-derivative one is the same as your gold sheet. But in case you're missing your gold sheet, you've got that. The trigonometric one is also on your gold sheet. I think it's a separate gold sheet. Parent functions, I think that just shows the shapes. If I'm not mistaken, there they are. So just different shapes. If you want that as part of your reference collection, that'd be good. And then there's these two review sheets that I've pulled off of my AP blog. This one is a few pages long, but it's actually excellent. It has all the derivative stuff, quotient rule, more derivatives, the inverse tan stuff, alternate definition of a derivative, equation of a line. I mean, it walks through all of it. It's filled out. I gave you the filled out version, but I also could put up the blank version if you would rather see that or fill it in yourself. But this would not be a bad one to kind of look over, especially it's got the nice theorems here, intermediate value theorem, mean value theorem, extreme value theorem, and Rolle's theorem. Those are the 4 main theorems that you are responsible for on the AP exam. So if using any of these, there is one we're going to go through as an MVT today. You have to satisfy that hypothesis. So you always have to address why you can apply the theorems. And then I doubt you guys will have to use those trig identities. That is more of a BC thing, but this first column is always a good one to remember too, like natural log of e is 1 and natural log of 1 is 0. Those sometimes we will see enter in. I would probably prefer to have the unit circle the whole thing because it's easy to read rather than a table format like that, but it's there. And then this one has the parent functions in it again. So that one is pretty comprehensive. So that, it would be a good one. Can't remember if this is, which one I think this might be the same one. That's the same one. Darn it, I had a 50-50 shot and I blew it. Okay, the first one. The first one I gave you when we started the review weeks ago. This might look familiar. It's another different format. It's just a front back one. It's got L'Hopital's rule in there, types of discontinuity, few derivatives, the theorems, those 4 theorems again, and then increasing functions, decreasing functions, max mins, all that good stuff. Speed, is speed increasing or decreasing? I like that in there because that often is something people screw up. Net distance, total distance. So both of those are pretty darn nice. If you want, I would print them out, look them over so you know what's contained on them. That makes them way easier to use. So those, I just loaded that file I kind of collected, went through all my stuff that I had and kind of picked out the best pieces I thought. So kind of generated a folder for you on that. So today I'd like to just go through that mixed bag one. Monday, or no, it was Tuesday. Tuesday we talked about the upload process. Are there any people using Chromebooks? So I went into school this morning. I've been at school since about 7:30 this morning. I just got home a little bit before we started our session. because I grabbed a Chromebook and I practiced with it. It's super easy. If you have one, I can walk you through it. Otherwise, what I intend to do is create a little video on that this afternoon and post it. It's easy to grab those files out of there. You'll just have to I would upload to my pictures to, there's Joey. I'd upload my pictures to my Google Drive, probably create a folder for it, and then it attaches very easily. You can browse and it just like snaps to the Google Drive folder. So that one's slick. Did you guys practice uploading? Yes. Did it go okay, Tori? Yes. Excellent. How are you going to do it? Are you going to bring it onto a laptop, or what are you thinking?
I'm just going to do it on my phone and write out my answers on paper.
Write out your paper. You think you'll be able to read it well enough on your phone? Yeah. Or, you know, air print it out so that you can lay it down too. All right. Good deal. Ryan, did you practice at all? Not yet. Okay. I really want you guys to give it a shot. Go on that AP website and do a little practicing on there. So that would be very sad to get to that day and have some issues. So, all right, well, let's just jump into this mixed bag review thing. The limit ones that start us off are kind of actually difficult ones. So they're good ones to look at. It's been a long time since we've done ones this hard. So they give us a picture. They tell us it is f of x, and it's made up of two line segments, blah, blah, blah. So part A, the limit as x goes to 0. A lot of people would be tempted to plug in 0 and say, okay, well then what's f of -1? And they would get 0, which actually is the right answer, unfortunately, on this one. But when it's a composite function like what we're seeing here, did I not send that to Smart? I got to send this over to Smart. Thought I had, but nope. Let me print this over to a Smart notebook so I can draw on it easier. All right, so when it's a composite function, you kind of want to work the inside first and then take that into the outer function. So give me 1 second, it's just about open. What I would do is write down the limit as x goes to 0 of x minus 1 and solve that inside piece first, like we usually do on composite functions, is work from the inside out. Yeah, it's not the cleanest, but that'll work. Okay, so I'm going to maybe just work off to the side and say the limit as x goes to 0 of x minus 1, the inner function, leads me to -1. And then I'm going to say that is, I'm going to use like a little bit of a u substitution. So I'm going to say that's u, just so I can document my steps. That answer, then I'm going to create a limit as x goes to, as x goes to -1, not x, u. As u goes to -1, and substitute in for u. So I'm working that inside. I know, doesn't that look nice, Evan? I saw your reaction there. Yeah, so we'll get that u to go into, so now we just have a normal function f of u, and this becomes f of -1, which then I can go to the f function and read at -1 and get the answer of 0. But it is kind of a two-step process on that. All right. Next, let's do the same approach on, I'll grab mine. Same approach. I was bothered because my answer says -1 on my sheet, which I think I just did a typo. It really is 0. So that was just looking at the official answer key to make sure I was not fooling myself, but it is 0. Next one, let's set up the limit as x goes to 0 of 2 minus x squared. And we can figure out what that inside composite function is doing. So if we plug in 0, that would say we are headed to 2. So now I'm going to replace this to u as u approaches 2, and then I can switch that to an f of u. Okay, so this will look like the limit as x approaches u of f of u. And we know that, whoops, not u there, as u approaches, and it'll approach 2, which in our picture is a bit of a dilemma because we have left and right limits. So now, if I think about the shape of 2 minus x squared, I would have parabola opening downward, height of 2. And as I approach 0, or 0 here, I'm coming into 2 from the underside, from below. So that would turn out then really to be, I'm approaching 2 from the underside. So then I'm going to come over here and talk about the limit of 2 from the left. And that then we can determine the answer is 3. I don't know if you'll get one of these complicated limits, but I thought you need to see these composite ones because they are tricky. L'Hopital's not so bad, but the composite ones are a little bit tricky. Work from the inside. Think about those shifts that are happening to our function. Kind of work that inside piece and then take that into the outer function. I'm going to leave C alone. The answer to C is 0 if you want to work it out, but ooh, should talk about that one. Yeah, we're going to move on because I want to get to some of these others too. Differentiation, chapter 2 for us. Given f of -3, f prime, and g, let h of x equal. Can you lay out what that derivative would look like? Take a moment, lay it out. See if you got this one right. I don't think it's going to be super horrible. It was just product rule, wasn't it? And this one didn't really have any chain rule in it either, so that was very nice. Now we just got to plug in, don't we? We want to evaluate this, what, at find h of, oh, let h of, oh, you guys, I'm really off. I was thinking that said h prime. I thought there was actually, for some reason in my head, I was reading find h prime of x, and then I thought I had a second problem. Okay, I'm going to backtrack a bit. I'm going to scratch that because you guys probably wrote something completely different out. Find the limit as x goes to -3, h of x minus h of 3. Ah, I probably will want that back, but when I see this, what does enter my mind is they're asking for the derivative of h prime, aren't they? That is the alternate definition of a derivative. And we are evaluating this actually at -3, because I can tell right there. I can tell right there. I can tell right there that all this stuff is going to -3, and it makes the 0 on the bottom. Okay, so we did really need product rule, but not for the reason I was thinking. So let me grab this and get caught up. Or g prime. Then I would just go into evaluating at -3 and throwing it into each of our functions. Showing the work as you do your steps. A lot of writing, but write fast. Write fast, but keep it neat. Pen, pencil, black or blue pen or pencil is acceptable on the exam. All right. And then I bet it's just going to be a ton of substitution, huh? So I'm going to end up with 4. F prime of 3 is -2. G of -3 would be 1 over -3. So a -1/3 plus a 4. G prime of -3. Looks like I got to go find my own G prime, doesn't it? All right, a little work off to the side. G of x equals -x to the -1. G prime of x equals -x to the -2, which restated looks like -1 over x squared. I needed to evaluate G prime at -3. So it looks like we are going to get -1/9. Actually, it's going to be, yeah, -1/9. The negative on top holds, the -3 gets squared, making it positive. And then f of -3 is 5. If you did not want to simplify, this is a perfectly acceptable answer just like it is. So I would just move on, save the time frame. Unit 3, stepping it up a bit, this is where the chain rule kind of comes into play. G is a differentiable function. The table gives values of G and its derivative, G prime at selected values. The function H is shown and it consists of 3 segments. Let K be the function defined by K of X equals H of G of X. Find K of 1, or K prime of 1. I'm gonna give you like 40 seconds to do this one, maybe even a minute. And then I'll jump on and tell you what the answer ended up being. To end up with something like that, you can leave your answer in that form. If you extended, I know 0.2 is the same thing as 1/5 or 2/10, and I could get this down to 1/10. So any of those representations, even 0.1 would have been fine. If you want to take a calculator, you don't have to though. So any of those 4 answers are going to be good. Let's look at part B. Are any questions on that? We're okay. All right. Part B, let M be the function defined by M of G of X equals X. In other words, M and G are inverses. Find M prime of 4. So what I need to do is remember how to take and do inverse derivatives. So if M and G are inverses, they want us to find M prime. I would probably go M prime of 4 is equal to, and it's equal to the reciprocal of its inverse function. So reciprocal means 1 over, and its reciprocal function is G, so G prime, but evaluated at M of 4, isn't it? So now what I got to do is figure out where I'm evaluating G at. G prime of what number? And this is the tricky part. They didn't give us an ordered pair this time. I like ordered pairs because that makes my life a little bit easier. So the only thing, there's no M chart, graph, or algebraic equation. There is a G chart though, right? And if M has the ordered pair for something, then G has what ordered pair? Something 4. So I can go to my chart, find the Y value of G. So G's Y value is 4, and then read the chart really in reverse and get that the X value had to have been 2. So now I'm doing a G prime of 2. And finishing this problem off, I don't know where that red ink is, there it is. 1 over G prime of 2 is 0.4. Not a real lovely answer, but an okay answer for the AP. If it really bothers you, I suppose you could convert and think 4/10 to 5ths and then reciprocate and get 5/2, but you don't have to go to that level. All right, inverse derivatives. It's the reciprocal of the corresponding inverse function, but evaluated at a different spot. All righty, given the differential equation, let's clean this up. dw dt equals 1/10 w minus 600. Find the squared, I didn't read that right, the second derivative of w with respect to t in terms of w. So I can't leave any dw sitting around. This is just taking a second derivative. Give it a little whirl. I'm going to give you about 20-second lead here, and then we'll talk about it. This isn't really that involved of one. They gave us a pretty simple function. But what I want you to realize is that is going to have to be implicitly derived. So I'd have dw dt, and then minus 600, that's going to zero out. You could have also, maybe some of you expressed it as w prime. That's fine too. Oops, I was going into second derivative. I got to indicate second derivative notation. So second derivative of w with respect to t, and I get this. But I can't leave my answer as w prime or dw dt. So what do? We just go back and substitute the first derivative back in, don't we? It replaces that. So I end up saying I've got 1/10 of what was dw dt, but it was 1/10 w minus 600. And there I can leave my answer at that spot. If you feel compelled, you could maybe simplify it one step. If you really feel compelled, you could take it all the way to that, couldn't you? Any of those three spots are just fine. So really read, they'll often say, you know, in terms of x and y, meaning I got to get all the way back to original functions or original variables. In this case, it was just get it back to w, okay? All right, let's look at unit 4. Applications of derivatives. At the beginning of 2020, a landfill contained 1,500, looks like tons of solid waste. The increasing function W models the total amount of solid waste at the landfill. Planners estimate that W will satisfy the differential equation, that one we just worked with, for the next 10 years. W is measured in tons and T is measured in years from the start of 2020. Use the line tangent to the graph of W at t equals 0 to approximate the amount of solid waste that the landfill contains at the end of April 2020. And I could count out January, February, March, April, and realize that's the 4th month. But our T is measured in years, so that is 4 out of 12. They gave you the T equals 1/3. I'm not sure that the AP would always do that. But we got this down. We know that T is equal to 1/3. So can we write an equation? Take a moment. See if you can figure it out. Encourage you to go back, reread stuff. Where was that tangent line being written at? What's its ordered pair? And what's the slope? Those are the two things we must have for tangent line. As you're calculating out your slope, we know we reference the derivative equation, correct? I'm evaluating this at T equals 0. So does T go in for W? No. W is the output when T equals 0. So it's this ordered pair. Think of this as a T comma W ordered pair. So what I really need to put in here is 1500, okay? That probably is the trickiest piece of this particular problem. So I'm getting 90 for my slope. Now I can write the equation of the line. Then second part is, okay, use that equation to approximate the landfill at the end of April. So we want to come in with T being 1/3. So we're going to use estimating process from our equation of tangent line. So I would probably go like Y of 1/3 is about 1500 plus 90 times 1/3 minus 0, or 1/3. And that answer is just sufficient as it is right there, down to multiplication and addition. If you just can't help yourself, looks like we get 1530. They didn't ask for the label, but it would be tons. All right, the next one. Taking it a little bit further with working with derivatives, this will probably get into max mins type stuff, maybe concavity too. At the beginning of 2020, landfill had the 1500. A lot of the stuff stays the same as the previous question. W is measured in tons, it's in years since the start of 2020. Use the line tangent to the graph to approximate the solid waste at time 1/3. We did that part. Find the second derivative in terms of W. We did that on that previous page, because I think that's exactly the same equation, isn't it? So we knew we had the second derivative. I'm just going to bring it into this workspace, was 1/10 of, actually it was 1/100th when we got said and done. I'll just go 1/10 of 1/10 W minus 600. Okay, so we got our second derivative. Find the second derivative. Use the second derivative to determine if the tangent line approximation is an under or overestimation of the landfill at time t equals 1/3. How do I figure out if a tangent line is over or underestimating? If I know concavity, then I can determine whether my tangent line is going to underestimate in a concave up scenario or overestimate when I have a concave down scenario. So I guess the whole meat of the question is, am I concave up or concave down at t equals 1/3? Well, concavity comes off of which derivative? Second derivative. So if I'm looking at second derivative, awesome, I have the second derivative. I just need to evaluate it at 1/3. So, but I want to evaluate it at 0 because that's where the tangent line was built. The 1/3 is the estimation of it, right? So we want to evaluate concavity at t equals 0, where the tangent line was originally built. So we're going to take our second derivative and evaluate it at time 0. At time 0, we did this evaluation, I feel like already. I'd have 100, the 1500 minus 600 makes 900 over 100, error, we get the number 9. 9 happens to be positive, right? It's bigger than 0. Concave up or concave down? Concave up. And for that reason then, our tangent line that was built at t equals 0 is going to lie below, and it's going to underestimate. If I just slid off to the right a little bit, t equals 1/3, where we did our approximating, well then our point is definitely going to be below the actual curve at t equals 1/3. So this is an underestimation. It didn't say whether you had to explain it, but your explanation would have to be a concavity argument. Okay. Just all you'd have to say is the function is concave up at t equals 0, and therefore the tangent line approximation at t equals 1/3 is an underestimate. Perfect. We've covered those before. Number 2, I like it. We're coming in with the MVT on this one. So good practice on one of those theorems. Verify that the function g of x satisfies the hypotheses of the mean value theorem on the interval -2 to 0. Find all the numbers x equals c in that same interval that satisfy the conclusion of the MVT. Oh, taking it an extra step even. All right. Verify the function satisfies the hypothesis. What is the hypothesis of a mean value theorem? Well, the hypothesis says that the function has to be continuous and differentiable. Is my function continuous and differentiable on the closed interval? Well, I definitely can put any number between -2 and 0 into my square root and maintain a positive argument under the square root. So I think it looks fine. I know what square root functions, behave like. This is where having like that parent graph printed out might be helpful. Okay, it's going to be something like this, right? Because it's shifted to the left by -2, and I know square root functions are like that. So this thing is definitely continuous and differentiable on the open interval. So it does satisfy the hypothesis. So the hypothesis, I could say that, what is the name of our function? G. G of x is continuous and differentiable on negative 2 to 0. What is the outcome of the mean value theorem? It's the one that says AROC's equal to IROC, or IROC's equal to AROC. I got my IROC on the left side, so the derivative, I guess we're working on G, so we'll go G prime. G prime of C is equal to G of an endpoint. I'm going to go 0 first. Minus G of negative 2 divided by 0 minus negative 2, so 0 plus 2. I got to take my numbers and throw them in, so I'd have square root 2 minus square root 0. So that's just the square root of 2 over 2, it looks like, for the slope on that. We also have to get G prime. So do a quick derivative on the square root function. Oh, so that's a 1 over 2, because 1/2 power comes down. And then it goes, subtract 1 will be at a negative 1/2. So that's going to build a square root of x plus 2. I think that's what it looks like. Maybe instead of x, I'll throw a c in there, since I was evaluating the derivative at c. Now, I guess it's really solving for c at this point. Maybe I'd square both sides. 1 over 4 times c plus 2 equals 2 over 4. Or 1 over 4, c plus 2. It's just a matter of solving for c. You do the steps however you wish. I'm going to cross multiply and get 2 equals c plus 2 times, I forgot my 4. Divide by 4. I'm at 1/2 equals c plus 2. Subtract a 2. And it looks like c is going to be a negative 1.5, negative 3/2. Now, is that value on the open interval negative 2 to 0? Yeah, it is. So that's awesome. Do we have to do anything to close this problem out, or was that it? Find all the numbers for c that satisfy the mean value. Yeah, we were able to come in with that. Looks good. And the main reason we were able to apply the mean value theorem is because we had a differentiable function. And I believe they talked about it being differentiable. Land waste, increasing function W, total amount of solid waste in the landfill. It has a differential equation for the next 10 years. So yeah, I think we're fine. Usually they make it a little bit more obvious that it's differentiable, like they usually state that it is, or it's a polynomial, or it's a nice little trig function, sine and cosine, where they're nice smooth curves. All right, what does part C, or part number 3 here say? Alpha of 1 equals 3, f prime is greater than 2, greater than or equal to. What is the least value for f of 4? Least value in my mind can be switched to absolute min. So now, how do I find absolute min? Looks like it's an increasing function. Then what is the least value for f of 4? What do they want us to do on this? I feel like it's almost just kind of build a tangent line. This one's a little crazy. Oh, because they don't give us an original function to work from. Yeah. I could write the equation of the tangent line knowing that the least slope is 2, which would then give me an approximation for 4, f of 4. That would be the smallest possible one. I kind of think that's what I would do. F prime of 2, or f prime of x is equal to 2. That would be its least slope. So from that, I can kind of conclude that m has to be bigger than or equal to 2. And then f of 4 would have to be less than or equal to kind of f of 1 or the 3 plus the slope times the change of the x values at 1. And then I could plug in 4 into that spot. It's a really different twist on a tangent line kind of application idea. Not really thrilled with that one. But yeah, so then I could calculate this and come up with 3 plus 6, 9. Like f of 4 will be less than or equal to 9. All right. Least value would be 4, or would be 9. And I think I'm going to leave that unit 6 one. I think I'm going to leave that one alone. I don't want to go through that one. All right. That took us like a half hour to whip through those. Are there other questions, or have you done any other reviews that you want help on or explanations for? There are loads of problem sets in that optional folder to look at. I know I've done this circuit training one. I think that was a pretty decent little review too, where it's one of those circuit problems. I think there's 12 questions to it. Working from a table. Really, really good practice working from a table. And then you kind of know if you're getting it right or wrong. If you can't get one of their answers, then you've got issues, right? I would suggest doing that for a little bit of practice. I think that would be good. What else did I have set up for? Nothing. Otherwise, there's that verbal STEM one too. I wrote down that that was good. Take a look at this verbal STEM. It's kind of similar to the problem we just did. This first one, you might even want to skip that. That's really similar to a problem that we just did. We've seen those types on the AP so many times, so that's why they just get hit a lot. But the particle movement one would be good. And the function one, tangent line, kind of similar. You're starting to see a lot of repetition because we've hit a lot of the important pieces. But there's a good one to go through. So hard to know what you guys need. You got to speak up. Unmute. Danny, how are you feeling?
I'm feeling good.
Good. Okay. Tori, anything you want help on? No, you're good. Evan? Feel fine? Jojo? Hallie?
I'm driving.
You feeling okay? All right.
Wonderful.
Yay! Bryn, I haven't talked to you in so long. How are you feeling?
Pretty good.
Pretty prepared? Good deal. Brooke Jackson, any questions?
Nope, I'm good.
All right. Joey?
I'm all right.
You feel okay? Okay. Well then, guys, I think the time has come. If I throw some extra sessions out there, I'll just throw them on updates, you guys, and I might pick to go through one of those verbal stems. There's like 3 of them. Verbal stems, I can't remember. There's table stems, and maybe I'll just sit and do a session, an open session with people if they want to jump on. Okay? Please, please, please practice the uploads. Because if you encounter a problem, call me, email me, Zoom me, anything, any of those. You can jump into, hour 4's Zoom or hour 5. I meet with hour 5 on Monday, so you can always jump in on that. Sam, how you doing?
Good. I was gonna ask, are you gonna do a video on how to submit? I think
Yes.
you talked about that earlier.
Yeah, I'll
Okay.
record that. You know what? I was at school and worked with the computer tech guide, Mr. Rogers, for about a half hour, 45 minutes this morning because we were working with the Chromebook, especially today. And then, I'll give an example of the Chromebook one. I'll give an example of maybe the computer, just working from a computer screen one.
Okay, sounds good.
Yeah. What device are you gonna open your test on?
Just a laptop, probably.
Yep. So then probably take your pictures and email it to yourself maybe, or do you think you'll throw it into Drive?
I can do Drive pretty easily.
Yeah. And then
Oh,
Drive maybe
hopefully
download to desktop. Because somehow you'll have to get out of Drive, right? That's the hard part.
Okay.
Because when you do your browsing for a file from on the AP Upload, it won't allow you to go into the internet side and grab Drive. And that's where our dilemma goes. So I would
Okay.
just Drive to maybe a desktop folder, and then I can go desktop to folder into the AP site.
Okay.
So that's what I'll probably end up demoing when I do that video.
Sounds good.
Sounds like a winner. All right. Danny, what are you going to use for your device? Are you laptop, desktop?
Yeah, I'm gonna use my laptop and then just take pictures of my phone and then airdrop it over.
So you'll be able to airdrop 'cause you got a Mac? Yep, perfect. That's probably the easiest. Yeah. Jenna, do you feel like you know what you're going to do for your uploads?
Yeah, I think so.
Okay. What about Linnea? Did she drop off? She might have just left. It's like, I'm out of here. Peace out. Hannah, are you set?
Yeah, I've done the demo a couple times, so I
And you're fine.
think I know
Okay.
what I'm.
You know what you're doing.
Yep.
Sweet. Hallie, do you need any help on how to upload?
Nope, I actually practiced a few times too, so I'm good.
So you feel confident? All right. Shay? Any?
I got it. I'm good.
You're good. All right. Sounds like most people are pretty set then. It's time to take a test, isn't it? You only drag it out so long. I just hope they give you guys decent questions and focus on the big topics. The max and mins, the concavity, tangent line, inverse derivative, all those nice things. I bet you'll see a L'Hopital too. I bet you'll see a L'Hopital rule. That would be, yeah. Because they can cover how do you do limits as well as how do you do a derivative. You can get a couple things for your, couple bang for the bucks there. So, all right. Anybody, do you have a test on Monday? Anybody for Gov? No, okay. So we'll be the first one then. Get it started. Sounds good. All righty, guys, I will say ta-ta. I'll end this meeting. Goodbye, you guys.